and welcome to Indonesia.
Let's continue to the next lecture by Professor Sulaiman Harun from University of Malaya, Malaysia, who will explain to us about fiber laser.
Professor Sulaiman Harun obtained his bachelor's degree in 1996 from the Technological University of Nagaoka, Japan. In 2001, he received his master's degree from Malaya University, Malaysia, and his doctorate degree from Malaya University, Malaysia. He is a professor Department of Electrical Engineering. Please welcome Professor Sulaiman Harun.
Okay, thank you adik-adik, mahasiswa. Okay, Assalamualaikum and good afternoon. Okay, first of all, I would like to thank organizer, especially Pak Alex, Pak Rahmat, Pak Henry, that invite me again to SCoMOA and also for the workshop. Okay, so today I will share my experience on fiber laser. So my lecture today is on fiber laser. So I am from University of Malaya. I think some of you know where is the University of Malaya. So we are located at the center of Kuala Lumpur. The #1 university in Malaysia. Okay, it's like ITB, #1 university in Indonesia. Okay, first, what is photonics? Okay, I think the previous lecturers or previous speaker have already introduced about the photonics, but I just introduce again. So photonics is the science of photon. So we know about the light, we know about the photon, the fundamental particles of the light. Okay, it's all start 1,000 years ago. When this Alhazen wrote the first book of optics. I think maybe before that they are study on optics, but our record only this one, the oldest, 1,000 years ago. So what you learn in the school, reflections, all these things. So actually it's from him, from this book. So it's not the new topics. So photonic optics is not the new topics, old topics. And this guy Al-Hazen wrote this book is actually in prison. So in prison, what they have only day and light, only light and darkness and light, only these two. So you don't worry if you have nothing. Even in prison, you can develop science. You can do research, you can do studies. So not necessarily you have very good facilities. You go to the big lab, so you can study anywhere actually. It's yourself. It's not the facilities. So you don't worry because Al-Hazen has made it 1,000 years ago. And to remember this, so UNESCO declared International Year of Light, 2015. So we have International Year of Light. Okay, go back to the photonics. So light is energy. So we know the photon has energy. So photon energy, H nu. Nu is frequency, H is Planck constant. So frequency is equal C over lambda. So H is constant. C also constant. The only variable there is only lambda. Okay, so you know lambda, right? So lambda is wavelength. So what is wavelength? What is wavelength? If you want to tell to your layman, so your atuk, you want to tell what is lambda? What is wavelength? Okay, maybe some student want to know want to know the answer. What is lambda? In the simple, in the daily term, lambda. daily terms. When you do science, you cannot think very complicated. The problem with us, you think very complicated. Because this thing has been invented, all science has been invented before. It's not complicated, very easy. Okay, so wavelength is a colors. Okay, color. Red have different wavelength, blue have different wavelengths. So what is the wavelength of the blue? 400. So red 600, green is 500 something, 550 and around that range. So the light is actually colors. So photonic is about colors, photon energy. Okay, so energy of the light depend on the colors. So the shorter wavelength, we have the higher energy compared to the longer wavelength. That's why a UV is very dangerous for your skin. Okay, because they have more energy. Because they're shorter wavelength, less than 400 is UV. Okay, so UV we have higher energy, so they will generate heat. Okay, they will generate heat, they will vibrate your molecule, your cell. If exposed to your skin, they will vibrate. So vibration can generate and distort, can change the structure of your cell, can cause cancer. Okay, go back here. So light is electromagnetic wave. Okay, they have electromagnetic. They are electromagnetic wave. They are both wave light or particle light. So they have duality characteristics. They are at the wave. So to explain light reflections, scattering, for example, you need to consider light as a wave. So to explain about amplifications, you need to consider light as a photons, as a particles, Otherwise, you can explain. So they have both characteristics, wave and also as particles. And light interact materials. So they will interact with the materials and structure. That's why we manipulate the light, so we can make many use application for the light, because light can interact with metal. Okay. Okay. Okay, first revolutions of photonics. So you know this guy, Tido Maiman, Ted Maiman. Actually, ignite the first laser, that is a ruby laser, in 1960. Okay, 16 May 1960. So the first laser was demonstrated. There is ruby laser. Here they use a ruby laser. They use a ruby rock. They use a ruby rock. Okay, they have flash lamps. So in those days, 1960, there are camera, a lot of cameras, you know. So camera use a flash lamp, flash lamp. So they use a flash lamp. So ruby rock, okay, to pump the ruby rock. So the implication here is because of the chromium ion. So ruby have the chromium ion. So they generate the first laser, that is ruby laser, red laser, working at 694.3 nanometers. Okay, so this because of the ruby, chromium ion. So they pump from using the flash lamp. So flash lamp actually absorb these two wavelengths, blue and green. Okay, blue and green, and emit at 694.3 nanometers. So these are the first laser. And to remember this, so UNESCO has declared, so we celebrate International Day of Light. 16 May, every year we celebrate International Day of the Light. Okay, so so even though this Ted Maiman have, you know, invent or demonstrate the first laser. He wrote paper, but he sent to journal. The paper was rejected. Okay, the paper was rejected. And today we cannot live without laser. Okay, everything got lasers. Okay, in this room we use so many lasers. Okay, so you don't worry if your paper get rejected, because that my mom also get rejected. Okay, so don't worry so much for paper publication, because we do research not just for publication. Publication is important to share your knowledge, but it's not your ultimate target to get published. So not necessarily people that publish a lot are better than you. Okay, it's not necessarily like that. Because we publish paper to share, so that people can respond, can give feedback, to get feedback. Okay. Okay, today, so the discovery of laser, so the laser is everywhere. It's used in telecommunications. Okay, we have very cheap telecommunication. Now we can communicate because of the optical communications. And in medical applications, in manufacturing, laser can cut metal, for example. And in future, we will have Wi-Fi. Wi-Fi can be 100 times faster. If you use light, 100 times faster than Wi-Fi. Okay, so it's used everywhere. Okay, what is laser? Okay, laser is a light amplification by stimulated emissions of radiation. The keyword here is a stimulated emission. Okay, keyword here is stimulated emission. What is a stimulated emission? Okay, some of you know what is a stimulated emission. I think you have learned in physics. What is stimulated emission? Okay, so stimulated emission is a process to generate. You have one photons. You generate two identical photons through the process of stimulated emission. A process to generate two identical photons. So if you have two photons, you generate four. 4, 8, identical. Okay, identical mean they are the same direction, they have the same phase, and they have the same energy, the same wavelength. So everything are the same, twin. So everything are the same. So you multiply the number of photons. That's why we get amplification, because you multiply the number of photons. The higher number of photons mean the higher intensity of light. Intensity of light depends on the photon. The higher number of photons, the higher intensity, the higher power of laser. Right? Okay, so the key word is here, stimulated emissions. So how to get stimulated emission? Okay, so you need to have pumping here. Stimulate, you need to have a population inversion first. Okay, so let me explain the laser first. So laser, they have three elements here. They have gain mediums. There is ruby laser just now. There is the gain medium is a chromium ion inside the ruby. There is the gain medium material. Okay, the material have band gap. So the operating wavelength of laser depend on the material. It's chromium 694. Okay, if helium neon is 632, 632.8. Okay, it's depend on the materials. So so this active mediums, and you need to have a pumping. You need to give energy, like in case of ruby laser, flash lamp. So you have another light. You need to shine to the materials. Material will absorb the light. Material will absorb the light. Okay, and then you need to have a resonator feedback here. It's two mirrors. It's two mirrors. So when you generate the laser, Okay, when you generate the light, the photon, when you pump, they will generate the light. They will generate photons. When you pump the materials, the material will absorb the energy from the pump. So the ion will move to the higher energy. So they will move to the higher energy to create the condition where we refer as a population inversion. So you need to have population inversion so that you can have the stimulated emissions. So when the photon coming, so they will generate two identical photons. But before that, you need to have the population inversion. Okay, so these three elements. So this here. Okay, so you have incident photons here. Okay, they will generate two identical photons. So this is laser process. It's quite straightforward. Okay, three interaction mechanisms are always simultaneously present. So when you to get laser, there are three processes involved. Absorptions mean you pump you launch the photon, so the material will absorb the photons. So the atom here we have the higher energy, so they move to the higher stage, okay, and then they emit photons because photon cannot stay very long at the higher energy level. They must release the energy, so they emit photon in terms of noise. They emit photon in terms of noise, okay. Because the lifetime here is very short. If lifetime is longer, so you will get amplifications. So when you have incoming without incoming photon, you generate amplified spontaneous emission. You generate noise in terms of spontaneous emission. So we call amplified spontaneous emission because this noise will be amplified in the materials. And if we have incoming photon, they will generate two identical photons. Okay, so the light will be multiplied. Okay, so we need to have the populations inversion. Okay, so to get the population inversion, the most important you need to have pumping. So they have various type of pumping. So you can use like in the laser diode. The pumping is actually you inject the current. Electrical pumping. Laser diode is electrical pumping. And in other type of laser, you can use this optical pumping. Optical pumping means laser technology means you convert the cheap laser, cheap light, cheap photon to the expensive photons, actually. So you need to have laser as a pump to produce the higher quality laser, more expensive laser light. Okay, so you convert the cheap light into expensive light. Okay. Laser diodes, because most of the pumping of the laser is done by the laser diode. So laser diode was invented in 1962. 1962, the first laser diode. So what is laser diode? So the material must be semiconductor. Diode means semiconductor. Semiconductor materials. So you need to have P material and N material, P-N junctions. So to generate laser, like this laser, for example, so it's made from the semiconductor. So the simplest structure, they have the P-N materials. I think you study in semiconductor what is a N-type material and P-type material, depend on the doping. Okay, how you doping, so you can make P material and N material. And if this P and N material you put together, they call junction, P-N junctions. You put layer by layer, so it's become P-N junction. And if you forward bias, you get light. Okay? Forward bias, you need to have battery. You need to provide voltage, forward bias, so you get laser come up through the process that we refer to electron hole recombination process. Because semiconductor, so the electron by pumping, so electron will move to the hole side, hole will move to the electron side, and then they recombine. So electron hole recombination can generate H nu photons. We generate photons. Okay, so this laser diode, even though the laser diode is invented in 1962, but the development very slow. There is no application. Why no application? The basic structure like that is require high currents. So you need to provide 20 amp to get very low power of laser. Okay, maybe 1 milliwatt equal. So the energy that required to generate 1 milliwatt is actually the same energy required to operate the aircon. So it's not practical. Until in 1970, around 1970s, there is a clever man, Alferov group, actually. They just innovate a little bit on the structure. They call heterostructures. So instead of P, only P and N, they have 2 layers, P plus and P minus, like that. 2P, 2N. So they make this type of structure so they can improve the efficiency of laser. Okay, laser diode. So they improve the efficiency. So they can so you can make laser very cheap. So in 1975, for example, 10 milliwatt laser cost about $250 US. Okay, so it's practical. So that's why we have communication. Because of this, we have communications. Okay, so we have communication because we have a cheap laser. So for communication, another important is optical fibers. So optical fiber, the idea is come from Charles Cow here. The first guy that saw the possibility to use optical fiber for communication. In 1966, okay, in 1970, the loss is 20 dB per kilometer. Okay, 20 dB per kilometer. So how much 20 dB? 20 dB, how much? You don't know 20 dB. In terms of percentage, how much the loss 20 dB? 3 dB is 50%. 90 dB is 90% is 10 dB. 10 dB is 90%. 20 dB is 99%. It's log scale. So you know it's 20 dB loss means 99% loss. Okay, 90% loss. So whatever you input 100 milliwatt, the output will be 1 milliwatts only. It's not practical after 1 kilometer. Okay, it's not practical in 1970. But because you know this glass technology, fiber optic is made from the glass. People make glass a long time ago. You know, if you go to Egypt, you go to Egyptian Museum, Cairo, you will see Pharaoh. You know Pharaoh, right? 6,000 years ago. So they have glass. They make glass, very beautiful glass. Okay, so it's because the technology is old. In China, people make glass a long time ago. People use glass. So it's very fast. Within less than 10 years, they can reduce the loss to the 0.2 dB per kilometer, less than 0.2 dB per kilometer. Okay, 0.2 dB, 100 kilometer, they have lost about 20 dB, 100 kilometers, 20 dB for 100 kilometers. Okay, so low loss. So it's practical for communication. So Charles Cow received the Nobel Prize because of his work in 2010, but he passed away 2010. So this optical fiber is perhaps the greatest optical gift to mankind. Okay, without the silica optical fiber, I think we don't have internet now, good communication. Okay, the world will be different. So God gifted to us because silica have low loss at 1.5. Silica have low loss at 1.5, and erbium. People use erbium to amplify. They have low loss at 1.5 micron, because communication we use 1.5 micron, and erbium we give amplifications at 1.5. So it's matching. So you have the medium that have low loss, and you can have amplifiers working at that region. That's why telecommunication people use 1.5 microns. 1.5 microns infrared. You cannot see the light. Okay, 1.5 cannot see. You know visible light range, right? What the range of visible light? $400 to 700. Very limited. God gave you very limited. 7. But you feel you are very big already. Very small. They give you only 400 nanometer to 700 nanometers. Very small range. Okay. So because you know fiber is made from silica, sand, abundant. So the price is very cheap, cheaper than spaghetti, and so much cheaper, almost free. Okay, so that's why we call the greatest optical gift to the mankind. And we have the second photonic revolution, optical communications. So people use optical fiber for communications here. So there we have transmitter, there is laser diode. So we have very cheap laser diode. Okay, in 1970s, so we developed, and we have receiver. So receiver is like the same like laser diode actually. Photodiode is same structure. So what difference between laser diode and photodiode? You have PN junction, you forward bias, you generate laser. If you reverse bias, you change the rotation of battery, you can use as detector. Okay, so detector just change the orientations of battery. Okay, so this detector. So now we have DWN networks. So optical fiber, the beauty of optical fiber, they can carry unlimited number of channels. Okay, you can carry many wavelengths, not only one channel. So through one single optical fiber, you can amplify. So you have many channels here, you can combine, amplify, drop. So these are DWN networks. Okay, so we have very cheap internet, and the technology for the communication now already matured. So the price of component very cheap. Okay, so now we can find another application. So all the optical component in the 1.5 micron region is very cheap. So light amplification. So light amplification important for the for communication. So it's an old story actually. So normally people use erbium ion. So you need to have erbium dot fibers. Okay, you pump with 980. So you have input signal at 1.5. So this signal will be amplified. Okay, so it's this. Okay, the same like laser. Laser you need to have two mirrors, closed cavity. So amplifier you need to have open circuit. Open, there is no mirror. You remove mirror, it's become amplifier. It's become amplifier. So amplification, as I said, because of the stimulated emission. One photon generates two identical photons. Okay, this old story. This so erbium dot fiber was introduced in Southampton University in 1985 by PhD student, I think. PhD work actually. And luckily they didn't patent, because they didn't patent the idea of EDFA. Otherwise, you need to wait 20 years. So maybe your generation still cannot have very fast internet. So you need to wait another 20 years. So luckily, because they compete. So thanks to this guy, erbium dot fibers. So these three people, David Payne, I think David Payne came here before as invited speakers. So he stood this guys, Giles, guys. Emmanuels. This is the way Emmanuels. So these three guys actually that work and develop optical amplifiers. So one in US, two in UK actually. So they use erbium dot fibers. Erbium dot fiber. So they dope optical fiber with erbium. So erbium, if you pump with 980, so you inject with 980. So the erbium ion will excite to the excited state. Okay, then they will fast decay to this metal stable state. Okay, and then they will emit light. When they go down to ground state, they will emit light at 1.5. Okay, they can emit light 1.5. They can use for amplification at 1.5 by using either 980 or 1480 nanometer pumping. So this is the structures. It's quite simple. You need to have three components: erbium dot fiber, WDM, to combine the pump light and the signal light. So you have these three components, you can make optical amplifiers. Okay. You know the demand for capacity is increasing every 2 years, doubling every 2 years, increasing every year. You know the more slow. So the demand for capacity doubling every 2 years, always doubling because we are not enough, greedy. You know, you need more capacity, more people use internet. So the engineer need to think how to increase the capacity of internet, because it's doubling every 2 years. So maybe now people use at 1.5 micron. Okay, people use single mode fiber, even though because they use erbium as amplification. So the amplifier range is only 100 nanometers. C band 400 nanometers, L band 40 nanometers. So another extra band is 20 nanometer, maybe 100 nanometers. Okay, so you can launch maybe 100 channel, 100 different wavelengths. If you do more, mean you need to reduce the spacing. Okay, the wavelength spacing, if you reduce the wavelength spacing, they can cause the foul emission. So these two signals will be interact. Okay, if the wavelength is too close, they may interact. Interact will generate another signal that can disturb the system. So you need to make sure the spacing above 50 gig. 50 gigahertz. 50 gigahertz, how much? 0.4 nanometers. 0.4 nanometers around. So frequency wavelength. You need to be able to, you need to know when we talk, whether we talk in the wavelength domain, in frequency domain, time domain. These three domains very important for optical engineers. You cannot be confusing, because they will be opposite. If you talk, so different domain is different things. So photonic crystal fiber is because if we use single mode, of course to use single mode is good. Okay, but one single mode, they can maybe support maybe 100 different wavelengths, 100 channel of wavelength. Okay, but frequency doubling every 2 years. So people try for the future communication system, maybe people use few mode fibers. Instead of one mode is 4 mode, for example. 4. Why 4? Because if you put more modes, more difficult to control, manipulate of that. So that's why you need to restrict number of modes. 4, maybe 8, so cannot be more. So this the future communication. How to get this is using the photonic crystal fibers. Okay, so these two guys that develop or introduce the photonic crystal fibers. This Russia and Jonathan Knight, these two guys. Okay, so they introduced this photonic crystal fiber for communications. So maybe to make the few modes or another applications in the high power laser. High power laser, when the power is high, you know the core size of fiber is only 9 microns. Single mode. You want to get single mode, you need to restrict to the 9 microns. Around 9, can be 6, can be 8. Okay, now 9 microns. But 9, if you increase the core size, the system become multi-mode. Okay, the system become multi-mode. But you want to have a single mode. That's why in the laser, if you generate power, for example, kilowatt, 1 kilowatt, or 1 megawatt, okay, it's very huge power. If the core size is very small, the power density can be very high. So the laser will generate heat, can melt the core, so can change the structure. So you need to increase the core size. So now people use large mode area fiber, LMA fiber. So how to make LMA fibers? You need to use this technology. So this, we know the fiber is, the light is guided into the core by the total internal reflections. But not only total internal reflection, you can use another principle, like band gap principle. Band gap principle to confine light inside the core. So you can make the core size larger, maybe 20 microns, maybe more. The larger is better, but maintain the operations of single modes. Okay. So these are features. Okay, game medium of laser or amplifiers. They have 3 or 4 level system. For example, NDA is 4 level system, and erbium is 3 level system commonly used. Okay, so maybe I go faster. Erbium is 3 level system, as I explained. You need a 980 nanometer pump, and to create so the photon, the ion we excited to excited state and fast decay to metal stable level to create the population inversion. When you have incoming light, so they stimulated the ion to go down to the ground state and emit two identical photons. So this is how the erbium fiber operate. And another game medium, for example, ytterbium. Ytterbium is used in industry, high power laser, because it's very efficient. Because they have two energy level system only. Okay, you pump with 975, they emit 1060. Okay, the pump and laser wavelength also very close, very close. So they can get the efficiency more than 95%, maybe 96, 98%. So you pump 1 watt, the output will be nearly 1 watt also. So it's good for the high power laser system. People use ytterbiums. And 2 microns. These 2 microns, you need to use another materials, thuliums here, or holmium, slightly longer wavelength, holmium. Thulium, you need to pump with 800 nanometers or 1200 or 1550 nanometers. Either one. Normally people use 1.5 micron. That is more efficient. So you get amplification at center at 1.8 microns, longer wavelength. Why we want to have the longer wavelength? Okay, the longer wavelength laser is actually for medical applications. 2 micron, 3 micron laser, people develop in the 3 micron, for example, is for medical application. Okay, why a medical application is important? If you want to ask money, you propose solution for 2 things. People will spend money only for 2 things: to kill people and to save life. You go to government, you know, for life. For example, you are very rich. if people say they can extend your life for 1 day, so they will give all the money. You know, you don't care about the money if come to your head. So when you want to ask money from the government, these two things. The keyword. Other is not important. These two things. Or the great invention, all because of two things. One, people in the war want to kill other people, so scientists become important. Because they need to kill people. So they need the scientists to develop the new way how to kill people. So these two field of research, very important. So normally in your proposal, these two very important for medical and for defense. Okay. So 2 micron is for medical because our body is a mix of water, 60% water, liquid. So the water we absorb at longer wavelength. Absorb where? The light at the longer wavelength. So when you do surgery, for example, is the laser because they absorb, so it's not damage other parts. Okay, it's not damaging other parts. So this very important. Mid infrared. A lot of people working on mid infrared region because of the medical applications. Okay, so these amplifiers. If you want how to make fiber amplifiers is compact. The most important you need to have dot fibers here. You have pump. So when you open the optical amplifier, they only consist of dot fiber. WDM, maybe you put isolators there. So this so depend on the structure. The gain depend on structure. So in the amplifier, the important is the gains and noise figure. Because when you have stimulated emission, you also have a spontaneous emission. Spontaneous emission, we generate the noise that we refer to the noise figures here. Okay, normally around 5 noise figures. Okay, so the gain depend on the input signal. Sorry, pump power here, but also depend on the input signal. So this example works on the optical amplifiers. So this how we design the broadband. Because the important, we want to make the compact device. So we want to have the erbium with the higher dopants. Because when you put more erbium in the glass, silica glass, they can cause clustering. Clustering is not good. Cluster, they can cause the spectral hole burning. Spectral hole burning means a certain wavelength we missing. Amplification, a certain wavelength we missing, spectral hole burning. So to avoid that, you need to co-dope. You need to put other elements in between so that it's not cluster. The erbium ion is not cluster. For example, we use here half neon bismuth. Actually, the element that we want only erbium. Other is actually to manipulate the lifetime, to manipulate to avoid the clustering effect. So we can make it very short. So this record we can get a 0.2 meters only. You get a 10 dB gain with the 0.2 meters. Okay. So if you use normal fiber, commercial fiber, maybe it require more than 1 meters. But this fiber, the beauty they can give, you can use only 0.2 meters to generate gain. And then the gain normally, if you use longer erbium, normally the gain will transfer from C to L. You can get the gain in the C band and also in the L band. Because L band operation involved because of the they have internet absorption there. So the erbium will absorb the C band light and emit in L band. So the gain in the C band will drop, so they increase the gain in L band. But somehow this fiber you can get in both. You can make flat gains in the both regions. Okay, these resonators, these some theories. So optical wave interfere when they are present simultaneously in the same region of space. So we know we have interference. Okay, when we go to fiber laser, so the fiber laser have either linear cavity, so this linear, or with linear cavity, or Fabry-Perot. We call Fabry-Perot cavity. So they have two mirrors here, linear or at the ring here. So in linear cavity, so when you generate lasers here, so laser will oscillate inside this cavity. So you will get the interference here, longitudinal interference pump. Okay, you can generate pulse laser by locking the phase. Okay, so light circulate or repeatedly reflect. So you need to have cavity resonator. So you have amplifier in the middle. So the light will be amplified, go to the end, reflect, amplify again, and reflect again, amplify. So amplification not only one time. At one time amplification, they can give gain, for example, 20 dB. But you amplify not only one time, maybe million times here. Okay, light oscillating inside the cavity. We call light oscillations. Okay. Okay, so if you want to generate pulse, for example, through mode locking, so the operating frequency depend on the cavity length. So the operating frequency depend on operating length. So resonator modes here, you have two mirrors. They can generate the standing wave here. Okay, the frequency of laser. So actually they create the mode spacings here. Okay, depend on the D here. D is the cavity length. D is a cavity length. So the frequency of laser depend on the cavity length. The standing wave that happen depend on the cavity length. So the longitudinal mode interference, so they will generate the standing wave, and this frequency depend on the cavity length. Okay, fiber laser. So fiber laser is introduced by Schnitzer here. Schnitzer in 1962, around that. Okay, 1960, a lot of laser developed. One of them is fiber laser, Schnitzer. Okay, but it's of course in the first fiber laser based on ND dot fiber. They dot the fiber with the neodymium ions. So ND dot fibers and pump with I think ND is 800 nanometers, I think, or visible light, invisible light. Okay, so fiber laser is actually you use optical fiber as gain medium. Okay, so the element, the ND element, for example, or erbium element is doped inside the core. Okay, so fiber laser is why fiber laser is important? Because first thing, no free space propagation. Because free space is quite complicated. If misalignment, so the laser power will be gone. So alignment is very difficult. You need to align the resonator, the cavity is quite difficult and easy to misalignment. So there is no alignment, so very easy. You just connect the okay, this one thing. So immune against the thermo-optical problems. They have the excellent beam quality because the core size is very small. Core size is 9 microns or smaller. So they okay, so they have a excellent beam quality. So fiber laser, normally the beam quality M square. M square parameter is equal to 1. M square parameters. Single mode. To get single mode is quite easy. If efficient, very efficient. Okay, because we use a diode pump operation, so they can provide high gain. So So this actually up conversion. You see, if erbium, you pump erbium, you see green, green color. Up conversion of the erbium, you generate the green color. This blue is a thulium. Thulium, you see the blue colors here. Okay, why fiber laser? They are compact, rugged, alignment free. The important is alignment free, exceptional reliability, high beam quality. Okay, so it's used in many applications here. So now, because the power, people can increase the power now. So you can get in maybe more than kilowatts output power. Now people easily get, and the power exceeding the free space, the bulk system. So it's exceeding. In those days, people use CO2 laser. When you want to do cutting, you use CO2. CO2 is problematic because it's gas laser. Gas is maintaining very high because this, like aircon, is easy to leak. Okay, so after 1 year, 2 years, they're leaking. So the efficiency of laser will drop. So gas laser. Okay, so CO2 is not good. So now the power of fiber laser so much higher than CO2. So that's why the like erbium, the efficiency is only 40 to 50%, but 50%. You won't get 90%. So this another 50 is because of up conversion of these things. Okay, so but ytterbium is 90%. Thulium is good because thulium also can give nearly 90% efficiency. Erbium, the because people use for communications. But efficiency is 50%. Okay, so you see the market also increasing, and the player also is more. So you can big market but small number of players. So advantage, as I said, fiber format, if you use fiber, high efficiency, direct pumping, compact, all this advantage. So the operating of the laser depend on the materials. For example, you want laser at one micron, you need to use ytterbium. Neodymium in 1 micron. So in 1 micron. Bismuth, a lot of people, especially Russian group, they develop because they want at 1.3. The second window of communication at 1.3. Okay, at 1.3 there is no amplifier. There is some amplifier but not efficient. So they want more efficient so that if you can get optical amplification in the 1.3, of course we increase, we reduce the cost of the communication. So bismuth, they target 1.3. Erbium 1.5, thulium is 2 micron. Erbium also in 3 micron. A lot of people do now in the, but the host material must be Ziblan, fluoride glass, Ziblan glass, not in the silica. In silica, you cannot get in 3 micron. So they must be in the Ziblan. Holmium in the mid-infrared also. So depend, the operating plan depend of the materials. Okay, various type of fiber laser. Okay, because limit of time, maybe I skip some of them. So we have nonlinear fiber laser. For example, brewing fiber laser, you can use nonlinear effect, brewing effect, to generate a very narrow line width. So this type of laser, they have very narrow line width. Okay, narrow line width laser have special other application. They have a lot of applications also. And Raman, they use Raman effect. So we have the nonlinear effect. We use a nonlinear effect. So Raman effect, Brewing is actually a nonlinear effect that you can use to generate lasers. So I single frequency laser like Brewing, they have very narrow line width. If narrow line width, you can make a single frequency laser. So this idea is like this. when you have the laser, so this uh, so they should be like this idea, sinusoidal wave, but they have coherence. They have coherent length. They are only maintained at the small regions. So this coherent length depends on the line width. If line width smaller, you will get longer. So they have longer coherent length, mean we call it like single frequency lasers. So single frequency laser, like this Brewing effect, how to get Brewing laser? So you need to launch light at this BP pump wavelength, for example. So you launch light at this wavelength. You will generate Stokes at 0.08 nanometer. 0.08 is 100 gigs. 0.08 is 10 gig. No, 10 gigs. 10 gigahertz spacing here. So they can generate Stokes through process of stimulated Brewing scattering. Okay, so this spacing depend on the materials. Of course, depend on the materials. Okay, so this example Brewing laser. So this is actually the setup here. Simple setup. So you get the Brewing laser. So Brewing laser is narrow line width laser. So the line width in the few hertz or less than kilohertz. Okay. So applications. Okay, so applications for the single frequency laser, for example, speed track. You can speed track using a Doppler effect. So you can measure the speed of the car. So you can measure when you launch the laser light into the car, because there is two moving parts here. Car moving, they have velocity, and your laser also have velocity. So we have two frequency. So they will generate another frequency Doppler effect. So you can measure. If you know one of them, so you can measure. Is higher wavelength able to have higher depth of penetration? So higher wavelength is they have more absorption, because higher wavelength, the water absorb longer wavelengths for medical applications. The water will absorb the longer wavelengths. Okay. So this example of a single application of single frequency laser. So you can measure speed of the car, and you can use for coherent beam combining. Okay, spectroscopy with high resolution if a narrow line width. So this example applications. Okay, and this laser, ytterbium dot fiber laser. So we did in our lab. So we have ytterbium dot fiber. So you have FBG here, function as mirror. Here also as mirror. So you need to have resonator, two mirrors. So one FBG, FBG can reflect light at certain wavelength, FBG. So another side, we use the Fresnel reflection. Fresnel reflection, when light propagate from the higher refractive index region to the lower refractive index region. So air have refractive index 1.0, glass is 1.4 to 1.5. So some light will be reflected. You can check, you can calculate, depend on the index contrast. There is equation lah. Now, very difficult to remember because everything in the internet. So if you don't know, you just Google search. So you can calculate the reflection. So normally it's 3.6%. It's glass to air. You will get, if you perpendicular cliff, so you get about 3% reflection. You will get easily 3% of reflection is enough to generate lasers here. Okay, so this will generate efficiency. How much efficiency? 88% efficiencies. How to get pulse? Pulse laser. They have two techniques: Q switching and mode locking. They have Q switch laser and mode lock laser. Q switch laser operate at kilohertz, frequency in the kilohertz, and spectral width of pulse duration is in the nanosecond to the microsecond. So normally it's bigger. Okay, it's nanosecond. The smallest they can go in nanosecond region, Q switching. Okay? And another type of laser is mode lock laser. So mode locking, so they can generate laser in megahertz, frequency in the megahertz, and the pulse duration can go into femtoseconds. Okay, mode locking you can generate from nanosecond to femtosecond pulse duration. So pulse duration is very small. So what difference? The principle also different. Q switching, you just modulate the intracavity loss. You have laser here, you put some element to modulate the loss, cavity loss, so you get Q switching. You can use modulator, you can use saturable absorber materials to modulate the loss. So you modulate the Q factors. That's what we call the Q switching. Q factor is loss, the Q factor of the resonators. So you can generate the laser in the nanosecond pulse. So the Q switch laser have the higher energy. So the advantage, they have the high energy peak powers. And mode locking is different techniques. Of course, you need to have some modulate the loss also, but you need to induce the fixed phase relationship. You need to lock the phase. You see light, the laser, when the laser oscillate in the core of the fibers, so the light go and come back, go and come back. So they can create the standing wave because of interference. You get interference, they will generate the interference. So the more, the higher number of mode that you can lock, the smaller pulse duration. Okay, so how good you lock? So there is more number of longitudinal modes that you together, so you get the smaller pulse duration. Okay. And the frequency for the mode lock laser is fixed, depend on the cavity length. But for the Q switch laser, it's depend on the pump power. In kilohertz region, but it's not fixed. It's depend on the pumping power. When you increase pumping power, the repetition rate also increase. Okay, so if you use saturable absorber, it's quite easy. So without saturable absorber, you get continuous wave laser. If you put the saturable absorbers here, you get the pulse. So saturable absorber is any materials. They will absorb light. You know, when the material absorb light, they will excite to the higher energy levels. And then they will be saturated because the number of ion that can stay at the higher energy level is limited. They will be saturated. When they are saturated, okay, so they will have they will modulate the loss. Okay, they absorb me high loss. And then when they saturate, they're not absorbing anymore, so low loss. So they modulate the loss from high loss, low loss, and the process will be repeated. Okay. Okay, this is the laser cavity. So you have gain mediums, erbiums here, gain medium, for example, depend on the operating wavelength. If you want to operate at the 1 micron, you use ytterbium, erbium 1.5, thulium 2 microns, and you put saturable absorber here, you get pulse. Okay, sometimes you put isolator. Okay, sometimes you remove because isolator can give loss. Isolator is like diode. Okay, they allow light to propagate in one direction. In one direction in the laser cavity. And then you characterize in 3 different domains. In the time domain, in the frequency domain, in the wavelength domain. Using this oscilloscope, RF spectral analyzer, spectrum analyzer, and optical spectrum analyzer. Okay, this example of Q-switch fiber laser. So this cavity. So this what you get the output. You see in the frequency domain you get like this. Sorry, in the time domain. Okay, you get this. From the spacing you can calculate the frequency, and then here you get these path durations here. Here 700 nanoseconds. And in the frequency domain, you see like this. The frequency here, the intensity will be dropped for the harmonics. This harmonic, the generic harmonic frequency mode and harmonics here. So this for the mod load laser different. Mod load laser they have many harmonic, more harmonic. But Q switch laser they disappear at the longer frequencies here. Okay. This nanosecond fiber laser is the same pattern of result. Okay. I think we have limited of time. So this is a pulse laser. You open here. So you have a circuit. You have a laser diode controller to control the laser diode. Okay. So this from optical components. So this for mod lock, the same setup, but you need for mod lock fiber laser, you need to consider the dispersion and nonlinear effects, right? Nonlinearity of the cavity. So this play important role. You need to calculate the dispersion. Right? Okay, dispersion play the role. Okay, so this example of this cavity. So you get like this soliton. You have a rectangular shape of the spectrum. Right? Okay, so this you see mod lock laser in this the frequency domain. You have a lot of harmonics here. So this show the path duration very narrow. So this here path duration is around 1.5 to 50 seconds. This very narrow, very narrow. Okay, so from this you know whether your path duration is narrow or not. Okay, so this example of the cavity we get this soliton laser because they have Kelly sideband here. This we call Kelly sideband, and you know the smaller path duration when you get the small path duration, for example, femtosecond region. So your spectrum will be broad here. You see, the spectrum will be broad, cover from 1555 to the 1585. So very broad. Okay. So spectrum will be very broad. So we get here 510 femtoseconds. Okay, so this in the time domain, this wavelength domain, the frequency domain. These applications of ultra short pulse lasers. So a lot of application. For example, in nanosurgery, for example, you know this. Okay, this therapy, optical communication, nonlinear effects. Okay, I think we have run out of time. This for continuum light source, you can use femtosecond laser, for example. If you develop for femtosecond laser, you can use, you launch into the photonic crystal fiber, microstructure fiber. You launch the pulse laser, you will get the broadband here. This broadband output here. This super continuum light source that people use widely in the spectroscopy. Okay, you want power broadband source. So how to generate? You need to have a femtosecond laser, and you need to have a nonlinear here, a photonic crystal fiber. You just launch, you can generate this broadband light source. Okay, so this another work. So for high power, you need to use double clad. fiber laser. So you need to pump it, you use multi-mode pumping. If you target for the high power laser, fiber laser, so you need to use multi-mode pumping. This multi-mode laser pump. So you need 5 pumps here because you need to pump very high. So the higher the pump, the higher the output. So as I said, laser actually you convert the cheap laser here. This pump laser is cheap, okay, to the fiber laser here that have a maybe single mode output. So high quality laser that more expensive. Okay, so this normally you combine many pump using the pump combiner. You have two gratings here, and you have the active mediums here. But because multi-mode pumps here, you need to use double clad fiber. So you pump through the inner claddings. They have inner claddings and outer claddings there. Okay, so this example of the application high power. So it's industry, drilling, for example, laser welding. This importance. So this can money come from this. You know, killing people. Okay. So this example laser welding. So you can weld. Okay, using the fiber laser. This is around 1 kilowatt. So it's very easy compared to the conventional welding, laser welding. Simple, you can do like that. So conventional, you need to protect your eye. Okay, so it's cleaner, it's easy to do. So this we develop laser soldering systems here. So we have fiber laser. So in semiconductor industry, so you need this soldering, low power laser. Okay, as conclusion, so the demonstrations of first laser has created the revolution of photonic field and has changed the world. And you feel it, the change now, the world has changed. Fiber laser have advantages of producing the low cost, robust, high quality, high power light source for various applications. Okay, so the compact optical amplifier can be obtained using the special fibers here. Brewing laser, we can also obtain using highly nonlinear fibers. So energetic pulse can be obtained via Q switching mechanism by modulating the intracavity loss inside the fiber laser cavity. So we can generate here 725 nanosecond pulse duration using this turmeric as saturable absorber. Okay, mod laser operating from picosecond to femtosecond have been realized in our laboratory. So high power fiber laser can be realized by using the double clad gay mediums in conjunction with the cladding pumping or multi-mode pumping. I think that's all because we have limited of time. So we have maybe 15 minutes for Q&A. If you want to ask questions. Okay. Okay.
Okay, thank you very much for Professor Sulaiman.
Okay.
So for online and on-site participant, is there any question?
Yes.
Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you for the lecture. It is a very good lecture. And let me introduce myself. My name is Riko Firmansyah. I come from Malang State University, MU, and and I want to ask about the basic principle, not about the fiber laser, but about the photonic that you mentioned earlier. That the photonic is like when it's less than the in the order of ultraviolet that could penetrate our skin and make a cancer. And I want to ask that how is that like how you describe that in the photonic way about that?
Okay, it's like nonlinear effect. You get nonlinear effects.
Or linear?
Nonlinear effects, you need to have high power.
Is that
You
thing
need
that
to have high energy power launched into the material.
okay?
So they will generate heat.
Hmm.
Okay, heat will vibrate the molecule.
Oh, I see. Okay.
Vibration of molecule, they generate acoustic wave. So interaction between photon and acoustic wave will generate the Stokes or nonlinear
Oh, okay. So
nonlinear
that
effect. In this case, also the same, because UV, we know UV because they have the shorter wavelength have higher energy. Okay, UV is shorter, but less than
shorter.
400 nanometer.
Yes.
So they have higher energy. So they have heat because UV make your skin dark, for example, darker,
Okay.
because they have higher energy. And higher energy can vibrate your cell.
Oh,
When
I
they
see.
absorb, your skin will absorb the UV light, and they will vibrate the molecule or cell there. And then when vibration, they will change the structures of your cell.
Okay.
It's one time okay, but many times you expose yourself to UV, of course, they can cause cancer.
I see.
Okay.
Yes.
Yes. Yeah, yeah, nice. Yes, yes. Photodynamic for medical applications. Can use also this principle. You can use for bad and for the groups.
Yes, I see. And the second question,
Yes.
if I may,
Yeah.
the second question is about fiber laser, but
Yeah.
it's more like the commercialized. Like you say, you provided data about there is some like enhancing market in fiber laser, but no Asian countries that has that had using that technology. And
Yeah.
what do you think about that?
Yeah, that's why I think in ASEAN there is no players so far.
Oh,
Nobody made laser and sell. So it's good, if we can develop our own laser and sell it.
because it's like a
But of course, a
advanced.
lot of cheap laser from China.
Oh, okay.
You need to compete with them. They make very cheap, very, very cheap.
I see. Yes, yes.
The price we dropping according Moore's law is go half by 2 years.
Okay.
Moore's law.
Okay.
The price
Okay.
go less every 2 years.
No, it's a clear problem.
That,
Okay.
go-
Thank you for.
Okay. 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 For biological applications. So photodynamic, for example, just now, I think maybe UV or it's not UV lah. People use like shorter wavelength region, maybe in the visible range. So depend on the application. You cannot say which is preferred. Say biology to kill cell. I forgot the wavelength, but normally because UV you want to use UV used in the manufacturing. Normally in manufacturing, photolithography use UV, but UV you cannot make fiber laser UV. UV is gas laser. There's a lot of work on the UV fiber laser because you can generate the cheaper source, so it's good. So because UV gas laser, gas is maintaining very high. So first question, second, the effect of polarization and stability on fiber laser. Okay, so fiber laser is of course the you need to control polarizations. If your saturable absorber is not good, okay, you can generate without saturable absorber also actually by manipulating of polarization actually. If you can actually you can generate pulse laser, Q switch or mode laser by modulating by manipulating the polarization actually. And but this type of laser is not very stable. Okay. So if you put shutter-body absorber, normally it become more robust, more stable. So this is important. But of course, horizontal stability play the role in some. So you need to fix all the fiber cannot be moved. Okay, so that the polarization state is not very significantly. Okay.
Okay, maybe from the on-site participant, there is still question.
Okay.
Thank you for the lecture, Prof. My name is Fritz Daniel from Pajajaran University.
Okay.
I was like watching the slides, and then I saw the last slide, which is I think it's a laser soldering system. I was wondering, like, people actually usually use conventional solder for like maybe like soldering electronic stuff. So I was wondering, what are the advantages of laser soldering system, and how does it work?
Because semiconductor, for example, chip like this. Okay, so if you use laser sometimes for soldering or desoldering to remove soldering. So soldering system actually because this very thin, so they not require very high power. So this laser system not high power, just normal laser diode. We use laser diode only, laser diode. But the important, you need to move the stage here. You need to program this engineering project. You need to program so that the point, because in the industry, semiconductor industry, you need to do many soldering. So you need to move. This should move according to the stage here. You need to design so that they hit the targets. So a lot of video on the YouTube on the laser soldering. I think you can see how people small because the chip is very small size.
So is it only for like soldering electronic chips, or we can use on anything like the conventional solder?
Yes, of course the market, we work for the market, of course, is for semiconductors, but of course can do to solder. So welding, for example, I show welding can use for welding. So I think in future people don't use a conventional way, or we move to the laser welding. Drilling, now people do drilling with laser. Okay.
Okay, that's it from me. Thank you, Prof.
Okay. 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 For fiber laser, how laser could maintain its mechanical strength? Because we use the laser is made from the silica glass. So silica melting temperature 1200. 1200. That's why they can, to generate heat to 1200 degrees Celsius is quite, you need very large power. That's why for normal power, maybe 200 watt, 300 watt, it should be okay, can sustain. But the problem is actually in the joint. If you join, for high power application, the problem at the joint. When you splice, you join one fiber to another fiber. And that joint, if the core size is not the same, of course, they will generate heat there. Heat will accumulate at joint. They can break. So the joint will be break. So that's why if no joint, so I think they can sustain. They can confine high intensity of light. But at the joint, so it's important. This technology there. The industry that know how to reduce, remove the heat, so they can make higher powers. Okay. second. Which way we can maintain circular polarized laser in fiber? Polarization, you need to use polarization maintaining fibers. If you want to maintain the polarization, you need to use polarization maintaining fibers. So PM fibers. Okay. Okay, in femtosecond, but it's not really. You cannot compare with the bulk system can make even shorter. Normally in the picosecond easily, but in the sub femto only. Sub femto, okay. Femtoseconds. So they have limited there. So far they have limited because you generate laser in the medium, like glass mediums. Okay, if you generate in the air medium, of course you can generate even shorter. Okay. Okay. Okay, any more questions? Or second question? Okay, Tensor-fire laser. So the bulk laser, fiber laser, as I say, the first is alignment. Alignment, the advantage is alignment and compact. Fiber laser is very compact. You can make very small, if smaller gain medium. So compact, alignment, robust, and maintenance free. Cost effective. So
Maybe from the on-site participant, still there is question?